Hello everyone, welcome to Multivariate Statistics and Machine Learning. In this video I will be discussing whitening transformations, which are everywhere in multivariate statistics, either explicitly or implicitly. So it's worthwhile to look at the foundations of these transformations. If you would like to study this from the lecture notes, you have to look into section 2.3. So, why are whitening transformations important? Simply because they make our lives easier. So, we've seen one already. So, one example. So, whitening transformations. So we've seen as example the Mahalanobis transformation, and the effect was we started with x, and x had some mean and some variance, and later x was transformed to y, and then this y had covariance equal to the identity matrix. So the individual components had variance 1 and there was no correlation. And why is this useful? Because this turns a multivariate problem into a set of univariate problems. So simplifies a generically multivariate problem or model into a set of univariate problems. Because we have, let's say we have d dimensions, so suddenly instead of one d-dimensional problem we have d univariate problems, and that is often much simpler to analyze than the multivariate problem with correlation. So let's look into general form. So the general form, so we have x is distributed from some distribution, and this distribution doesn't necessarily need to be the normal distribution. It can be any distribution, just the distribution has to have covariance, of course. So it has to have first two moments, and then our aim is to have a transformation. So we look at a linear transformation Z equals a matrix W, so that's our whitening matrix times X. So it's actually even simpler than the Mahalanobis transformation, so because we don't have a scale thing. And the aim is to have the variance of Z to be equal to the identity matrix. So the question is how to choose this matrix W. So this is the whitening matrix. So how do we choose this? And one solution we know already. So if we, for example, we could choose W is equal to sigma to the power of -1/2. So that is one solution. But it turns out there are plenty of other solutions, and in fact there are many solutions. So, and we can work out the solutions by basically going backwards. So we start with this constraint. So the variance of Z is equal to the identity matrix. So this means we have the variance of Wx is W sigma W transpose. This is the identity matrix. So this is simply applying what's written there. And if we now multiply this with W, we see that W times sigma times W transpose W equals W. And if we carefully look at this, we actually realize this must be 1, or not 1, the identity matrix, so that this is actually true. So we have as a constraint on the whitening matrix on the following condition, namely that the whitening matrix transpose times the whitening matrix is equal to the inverse of the covariance matrix of X. So that's our constraint. And we can easily see that the Mahalanobis constraint, Mahalanobis solution actually fulfills this. So if we, because this is symmetric, so we get this times this is the inverse of the covariance matrix. So satisfies this constraint. So the question is, can we find others? Are there others? And the answer is easy. Yes, there are others. Yes. And the solution, the general solution, so solution to this constraint is simply this solution. So we can write any whitening matrix as the product of a rotation matrix that I call Q1 times the inverse matrix square root of the covariance matrix. So basically, so Q1 is orthogonal. So we can choose a whitening matrix by choosing Q. And if we set Q equal to the identity, then we get Mahalanobis. Mahalanobis. But if we use any other Q, and there are infinitely many rotation matrices, then we can get different whitening matrices. And it also works the other way around. So every whitening matrix you can find a orthogonal Q simply by solving this equation for Q, and then you can show that the given sigma and giving a whitening matrix that satisfies the above constraint, we can compute a Q, and this Q is an orthogonal matrix. So this is one way to write this. So another way to write this, another way is the following. So we can write the whitening matrix as the product of Q2, so that's a different rotation matrix, times the correlation matrix to the power 1 minus 1/2, so this inverse matrix square root of the correlation matrix times the inverse matrix containing the correlations. So recall that sigma is written as the product of V 1/2 rho V 1/2. So this is the variance correlation decomposition of the covariance. So, and with this decomposition we can write the whitening matrix as follows. So we can also this also satisfies this constraint as it can be shown easily. Just plug it in, then you see that you'll get the inverse of the covariance matrix. So you can, so basically the summary, there are infinitely many whitening transformations, and we can choose them by choosing a rotation matrix. Choose one by selecting Q1 or Q2. So the question is really, how do we actually choose Q1 or Q2? So how do we pick Q1 or Q2? And we can pick Q1 or Q2 by looking the effect of Q1 and Q2 on a different thing that we haven't looked at so far. Namely, we can look at the covariance or cross covariance or cross correlation between Y and Z. So we have Y, not Y, we have it's called, we have Z and we have X. So the name, it's called Z here because Z usually is the name when you have latent variables that have unit variance and aren't correlated. So Z is our whitened variable and X is the original variable, and we can now look at cross covariance. So the cross covariance is simply the covariance between Z and X, and we call it phi, and this cross covariance is covariance of Wx and X and you can see easily it's simply this. So it's the product of the whitening matrix times the covariance matrix, and if we plug this in further, our solution for the whitening matrix, we end up with this formulation. So the cross covariance between the whitened and the original variables is simply the product of Q1 and the covariance matrix. And we can do the same for the cross correlation. So the cross correlation we denote here by psi. So it's the correlation between Z and X, and that's basically the same thing, because it's simply phi, and then we standardize it, or the variance. I mean, X needs to be standardized, Z doesn't need to be standardized because it is already standardized. And if you plug this in, then it turns out then you get Q2 times the matrix square root of the correlation matrix. So it basically looks exactly the same as the cross correlation, cross covariance. Only that it's now expressed in terms of the correlations rather than the covariance. So this shows also the meaning of Q1 and Q2. So Q1 is the rotation factor for the covariance, and Q2 is the rotation factor for the correlations. So in the next session, I will look into a couple of several choices for Q1 and Q2, and these choices will be guided by the values of the cross covariance and the cross correlation. So for now, in the last bit in this session, we'll simply look at some of the properties of the cross correlation. So the cross correlation, if you just from the definition, of course, you see that psi transpose psi gives back the correlation matrix, and hence the diagonal of this thing, psi transpose psi, is the vector of all the with all the ones on the diagonal. So the trace of this thing is equal to the dimension d. And this actually has an interesting interpretation, because this means that the column sums, so if we look at the elements of the psi matrix, so this is our psi matrix, and it has elements psi ij, so it's a little bit tricky to do this in handwriting, but this means basically, so the first thing means that the sum of the columns, so if I sum over the individual components and square them, these are all 1. And this means that the squared correlation of the whitened components with the original components, that they sum up to 1. And that's interesting, of course, because this is actually the meaning of the R squared coefficient. So the R squared coefficient from the whitened going back to the original is always 1. And that's of course not surprising, because we don't have a dimension reduction here, but we just have an invertible transformation. So we can just go back and we don't lose anything. So that's it for today. So hope you found it interesting. And in the next session we'll be diving deeper, and we will apply this general form of the whitening transformation to a number of specific whitening techniques that are commonly used in multivariate statistics and in machine learning. Until then, bye bye.